Okay, good morning. Slowly I'm figuring out how to use OneNote and everything, so yay me. It's been a bumpy road. All right, let me just close this because it's a little distracting. Okay, good. Just reminding me that we have class, and here we are. Okie dokie, artichoke. So what we're going to do is we're just going to start, we'll do review by way of example today, just because what we developed last day, things like the reference numbers and the terminal points, all that kind of stuff, we'll just see in some examples here. So in terms of review by example. So if I ask you to find the terminal points of A, t is going to be 7 pi divided by 4, and B, t is negative 2 pi divided by 3. I'm trying to keep them side by side. It gets tricky sometimes, but just so you can see how they're playing out next to each other. Okay, so we talked about those core cutoff points, right? Of course, on the unit circle, we've got our chord array marks, right? But also we talked about the cutoff points at pi over 6, pi over 4, and pi over 3, right? And so, and I told you had to memorize those, and so we should have those memorized, right? Or know to have them memorized eventually, right? But for a little bit now, right, we can draw our unit circle here, and we can say, okay, well, this point here is at 0, 1. This point here is at negative 1, 0. 0, negative 1, and 1, 0. We also talked about splitting this thing into pi over 6, which was at the point, let's see if I can remember, root 3 over 2 and 1/2. And then I know pi over 3 is the switcheroo of those. 1/2 root 3 over 2. And then pi over 4 was at root 2 over 2, root 2 over 2. Right? So we'll just kind of use those, our reference numbers. So 7 pi over 4, if we have to map it out on the unit circle, I just kind of make a note of how far it is from being maybe 2 pi or pi, depending on what's closest. 7 pi over 4 looks awfully close to 8 pi over 4, which would be 2 pi. So I know I'm getting closer to kind of a complete cycle here. So I can go around, oops, and freshen this up. It looks to me, right, like if I just went another quarter, then I would have a full revolution. Let's do a different color here. There. So here, our reference number we say is t bar. T bar is going to be pi over 4. Pi over 4 from here we know is at the point root 2 over 2, root 2 over 2. And then in quadrant 4, right, this is quadrant 4. We also know that, okay, well, my x's are going to be positive, and my y values are going to be negative, right? So let's see here. The reference number t bar is pi over 4, which has a terminal point at root 2 over 2, root 2 over 2. But since we're in the fourth quadrant, right, our x must be positive and our y must be negative. But since we are in Q4, and if you prefer to just write 4, that's fine. Roman numerals, you don't have to. Our x is positive and y is negative. Therefore, the terminal point, right? Find the terminal points of 7 pi over 4. Therefore, the terminal point of 7 pi over 4 is positive root 2 over 2 and negative root 2 over 2. So we use all that knowledge about where x is positive and negative and where y is positive and negative, and then we can just use what we know from the first quadrant and apply it to all the other quadrants, right? So let's do the other one. So we remember, or maybe we need a refresher, it is the review after all. If we have a negative angle or a negative distance, then we're moving clockwise instead of counterclockwise, right? And so what we have is we'll have something that looks like, like this. Okay. So if I've moved negative 2 over 3 clockwise, right, I can split my lower half into thirds if that makes more sense to you, right? So here's 1/3 of the way and here's 2/3 of the way. I'm missing a distance of 1/3 to complete this negative 2 pi over 3. From the closest x-axis, right, that's the negative x-axis in this case, we're going down a distance of pi over 3. We're missing a distance of pi over 3 to make that full pi. Our reference numbers are always positive, right, because they're just referring to where we are in the first quadrant. Okay. So, again, the reference number t equals pi over 3 has a terminal point pi over 3, right? If you remember it, that's great. If not, right, you can refer to this little sketch that we have. It's at 1/2 root 3 over 2. Root 3 over 2. Okay, here we're in Q3. In Q3, both my x and my y's are negative. So in Q3, both x and y are negative. Therefore, the terminal point of negative 2 pi over 3 is negative 1/2 negative root 3 over 2. Okay. So what you'll find is we're going to use these x and y values to figure out what trig functions are. So you probably remember sine, cos, tan, right? So katoa, that kind of stuff. So we're going to use these x, y values to figure out what the sine and the cosine is of something like negative 2 pi over 3, for example. Yeah. So that's what we're building towards. Okay. So that's where we got to last day. So I'll call that the end of our review, right? You can go through and look through the notes because there were a lot of definitions that we went through last day that'll come back up. So hopefully that'll help us kind of remember some stuff. Okay, so we can finish this section here, by saying, okay, we know that the circumference, we already established that the circumference of the unit circle is just 2 pi, right? A distance of 2 pi gets us around the circle once. So if we're starting at a point t, any point t on the unit circle, if I move a distance of 2 pi, it puts me back to that point, okay? And so we use that to say, well, if I know kind of the original distance, and then if I've tacked on a bunch of 2 pi's, right, then the terminal point is always going to be the same, right? As long as I'm moving a distance of 2 pi around that point. So since the circumference of the unit circle, is 2 pi, okay, we know that t and t plus 2 pi, t minus 2 pi, right? Or just in general, t plus minus 2k pi, or let's do n pi because that's what we use later, lowercase n pi, where n is an integer, right? An integer is just a whole number. It can be positive or negative, right? But so every kind of counting number is an integer. So 1, 2, 3, 4, 5. And so if I move 5 multiples of 2 pi, I've just gone around the circle 5 times, right? You can even have negative, but because we've got this plus minus, it's already kind of taken care of. This is how we could write it, and I should kind of make this cleaner. N is in the set of integers. Right? That's from way back. But that's how we're going to write it, right? So if n is in the set of integers, then n can be anything from negative infinity to positive infinity, but only whole numbers, right? Negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, blah, blah, blah. Okay. So what happens is that all of these, right, all these values have the same terminal point. All these values of t, all these values, it got confusing, right? Because I've got t plus 2 pi, so I'm not really talking about t. So all these values have the same terminal points. have the same terminal points. Okay. So that's something we're going to keep in mind, right? We're just looping around the circle. So let's do an example where we use that. And I'll admit it can be a little bit tricky to kind of wrap your head around pulling out multiples of 2 pi, right? But if you just kind of ignore the pi, don't forget about the pi. But if you just kind of ignore it for a little bit, it'll make it a little bit easier, I think. Right? But we'll see how you find this example. Find the terminal point. Find the terminal point of t equals 29 pi over 6. Okay. So what we do is you're going to pull out multiples of 2 pi. So here, I'll just write it as t equals 29 pi over 6. Pull out multiples of 2 pi. Okay. 2 pi over 6 is really going to be 12 pi over 6, right? So you want to match this, this value here. Okay. So you can break it up as long as you keep that common denominator, and that's why we worked, or it's not why we worked through, but it helps that we worked with so many fractions already, right? Because we know we need common denominators. So what I can do is I can rewrite this t as 12 pi over 6, right? 29 minus 12, oops, I did 13, huh? Is 17, so plus 17 pi over 6. Looks like I can still pull out a 12 pi, right, from 17. So this becomes 12 pi over 6 plus 12 pi over 6 plus 5 pi over 6. So here, right, I've got 2 times 2 pi. All that's saying is that I'm going around the circle twice and then moving a distance of 5 pi over 6. Right, so here, go around the unit circle twice. Then move a distance of 5 pi over 6. Okay. So what does that look like? Well, we can draw our unit circle here. So what I've done is I've gone once around, twice around, and then I'm moving 5 pi over 6. Okay. 5 pi over 6 is really close to 6 pi over 6, which would be at the halfway mark, right? So I just need to move a distance of 1/6. So it looks like maybe to there. So then my t bar, my reference number, is going to be pi over 6, right? That's all I need to move in addition to 5 pi over 6 to get to that negative x-axis. So it doesn't actually matter how many times you loop around, right? You're going to end up at the same terminal point. And so we use that. We just pull out multiples of 2 pi, and then we see where we end up. Okay. So from here, right, we've got pi over 6, or I'll say t bar is pi over 6. Pi over 6, and I'm just going to say what the what the point is for pi over 6. It's at root 3 over 2, 1/2. Okay. But in cube 2, there, I did it. Not using Roman numerals anymore. You can, I can. I'll switch back and forth just to kind of be inconsistent, I guess. No, but we can move back and forth between them. So, but in cube 2, x is negative and y is positive. X is negative, right? I'm not going to talk about the y because it doesn't change. So the terminal point of t equals 29 pi over 6 is at negative root 3, 2, and 1/2. Good. So now we've established the basics for moving around the circle, the unit circle. We have some check-in points. So now we're going to use these x, y values as promised to figure out some trig functions. So section 5.2, I have no idea where the page breaks will be generated, so I guess there's that on here. So 5.2 is going to introduce trigonometric functions of real numbers. So we're just going to start right off the bat and we're going to define some of these trig functions. And so what we need to do, definition of trig functions. Oops. First, we have to establish, so t is going to be any real number, and t is going to be the same that we've been talking about. It's the same t that we've already been talking about, right? It puts us on somewhere on the unit circle. So we're going to let t be any real number, and let p, x, y, so the point p, you don't really need the p in front, but it just helps emphasize that it's a point. Okay, let p, x, y be the terminal point, on the unit circle, determined by t. So that's what we've been working on. We've been working on finding that point p, x, y, right? Determined by t. Oops. Oh, clean that up. So what we're going to do, we define sine t is going to be y. And it's exactly the same y that you have in your point. Okay, that's useful, right? Because if you know pi over 4, if t is pi over 4, for example, then x is root 2 over 2 and y is root 2 over 2. So then the sine of pi over 4 must be root 2 over 2. Right, so we already know how to find a lot of these values now, knowing that sine t is the same as y. Cos t is going to be the same as x, and I'll just highlight that they're the same, right? So the x and the y that I'm talking about now, they're the same from that point. right? And the t is the same as before too. So tan of t is going to be y divided by x, as long as x is not equal to 0, right? We can't divide by 0. So we have to keep that in mind, right? It also means that there are some places where the tan of t is not defined, right? Especially if you think about your unit circle, there are 2 points where x is 0. We'll come back to that when we talk about the domain, but it's just something to keep in mind as we go along here. The other two, cosecant of t is 1 over y, as long as y is not equal to 0. Secant of t is 1 over x, as long as x is not equal to 0. Cotangent of t is x over y, as long as y is not equal to 0. So notice that there are 2 functions where x can't be 0, and there are 2 functions where y can't be 0. So they'll have the same domains. Okay. So let's use this, and we're going to find, so as an example, find the 6 trig functions. So these are the 6 trig functions that we have. In fact, you know what? How about we highlight this nice and bright here. It actually acts like a highlighter, pretty fun. Whee! You'll definitely want to have these handy, just like those cutoff points, right? Those terminal points that we established last day. You'll want to have this handy, and together we'll build all these different trig functions. So find, oops, probably not in highlighter. Find the 6 trig functions for t equals pi over 3. Okay. What's nice is we already know pi over 3. Okay, so we've moved pi over 3 in the first quadrant. We know the terminal point. We know the terminal point of t equals pi over 3 is, and just to emphasize that it's the same p, we can put the p outside. We haven't really been doing that, but that's okay. It's just to say this is a point on the unit circle, is 1/2 root 3 over 2. So just to highlight here, so x is 1/2 and y is root 3 over 2. Knowing what x and y are here, I can plug those in and I can solve for the tan of pi over 3, the cosecant of pi over 3, the secant of pi over 3, right? Because t here is going to be pi over 3. So wherever you see a t, you're going to replace it with pi over 3. Okay. So what that's going to look like, sine of pi over 3 is y, which is just from up here, right? Sine of whatever is the y value. And so sine of pi over 3 is root 3 over 2. Good. A lot of the time, especially in calculus, if you go on to calculus, you'll need to be able to give the exact values. Your fancy calculator, this one, it gives you the exact values, I'm pretty sure. Sine of pi over 3. We'll get to it using your calculator, it does. So that's really nice, right? You'll be in Radian modes or Radian mode for this, and we'll get there. But for now, right, I want you to get really comfortable just using the unit circle to figure out what these points are. So sine of pi over 3 is y, which is root 3 over 2. Cos of pi over 3 is x, right, from up here. And so the x value is 1/2. Yeah. I'll just do 2 on each line, otherwise it gets too messy. Tan of pi over 3. Tan of pi over 3 is y over x. We have to make sure that x is not equal to 0. In this case, x is 1/2, so it's okay. We're not going to divide by 0, so we're safe. Right? So it's y over x. Y over x is going to be root 3 over 2 divided by 1/2. We've got a fraction over a fraction. We know what to do with a fraction over a fraction. So we get root 3 over 2 times 2 over 1. That's just going to put me at root 3 by the time the 2's cancel. Okay. It's the next one on the list. Cosecant. We have to make sure that y is not equal to 0, right? And in this case, y is root 3 over 2, so we're safe. Cosecant of t. Oops. T we're replacing with pi over 3. Cosecant is 1 over y. 1 over y, there. Which is 1 over root 3 over 2. One over root 3 over 2. If I flip and multiply, I get 2 over root 3, okay? But one thing to keep in mind is that we rationalize the denominator, right? And so we always want the root in the numerator. So what we do, we've done this before, right? If we have to rationalize something, then we multiply it by the conjugate. In this case, it's going to be times root 3 over 3, or sorry, root 3 over root 3. Rationalize, oopsie daisies, rationalize the denominator. Okay. So if I have root 3 times root 3 in the denominator, then I have 2 root 3 over 3, right? So I've just bumped that. I haven't changed the value, right? I've just bumped the root into the numerator. Okay. So that's cosecant. Next one I'm going to do is the secant of pi over 3, which is going to be 1 over x, as long as x is not equal to 0. We've already checked that, so that's good. 1 over x, which this keyboard keeps popping up. 1 over x is 1 over 1/2. Fraction over a fraction, right? I flip and multiply. That just puts me at 2 over 1, which is 2. And then finally, we're going to do the cotangent of pi over 3. The cotangent of pi over 3 is x over y. As long as y is not equal to 0, but we've already checked that. X is 1/2. And y is root 3 over 2. I've got a fraction over a fraction. I can flip and multiply. And so I get 1/2 times 2 over root 3. This 2 is going to cancel with this 2. And then what I have to do is I have to move that root 3 upstairs to the numerator. And so I'm going to multiply by root 3 over root 3 until I finally have root 3 divided by 3. Okay. Good. So this, right? We're doing the same thing again. Right, so you don't want to have a root in the denominator. That's all we're kind of trying to avoid. Okay. And how do you do that? Well, you look at what you want to move upstairs, and then you just take, wait. There. You just take that thing and put root 3 over root 3 or whatever root you have over itself. Okie dokie. Let's do another example because we had to check whether we were dividing by a 0, right? So let's say if we have to find the cos of pi over 2, the sine of pi over 2, and the tan of pi over 2. Okay. So the cosine of pi over 2, if we just think about our unit circle here, right, pi over 2 would be this distance, putting me at 0, 1, right? So x is 0, y is 1. So that means that cos pi over 2 is 0. Sine pi over 2 is 1. And tan pi over 2 would be 1 over 0, right? Y over x. Undefined, or sorry, I'll say the whole sentence. Tan of pi over 2 is undefined since we can't divide by 0. So that means that we're going to have some sort of vertical asymptotes, right, for tan. And you can graph tan of x in Desmos. I don't have Desmos on this one here, so I'll hold off until my iPad's back. But that'll be perfect timing for when we're talking about graphs, right? But we know if something's undefined, right, we're going to have these vertical asymptotes at those points. Okay. So what we can do is we can draw our unit circle, kind of like this, right? And if we've got our x and our y values, then what we have, let's do, at these 2 points, y is 0 here and y is 0 here. So we know that there are 2 functions, right? Scrolling back up, if I can even scroll, there we go. If y is 0, then my cosecant and my cotangent are undefined, right? And so that's something I need to keep an eye out for. But also if x is 0, right, then my tangent and my secant are undefined. So let's just kind of look at what that looks like. So at y equals 0. Y equals 0 at n pi. Oops. And I'm going to use that notation that we reminded ourselves of what it meant, where n is in the set of integers. And the z with the fancy back. Okay. So, right, as long as I'm moving n pi, so I start at 0 pi, that's at 0, and then I move 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, blah, 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 right? So at all those points, y is going to be 0. Same thing up here, right? Just looking at your x and y axes, x is 0 here and x is 0 here. So x is 0 at pi over 2 and 3 pi over 2. But notice that, again, we're just moving a distance of pi, right? So it's really just pi over 2 and then multiples of pi, right? Or pi over 2 and then multiples of pi. So what we say is we have pi over 2, so x equals 0 at pi over 2 plus n pi, where n is in the set of integers again. Okay. So we use this to establish our domains, right? Because there are some domains that are undefined if x is 0, some that are undefined if y is 0, and some is just all real numbers because it doesn't care. There's no division. So we use this to establish the domains. So we know from before, if I can scroll up there, right? Sine and cosine have no restrictions on the domains, right? And then we said that tan and secant are going to get lumped together because they have restrictions on x, and then cosecant and cotangent have restrictions on y. So what we say is that sine and cosine have a domain x is in the set of real numbers, right? So it can be any number from negative infinity to positive infinity. Tan and secant, right? Are undefined where x is 0. Undefined where x is 0. So I guess I can't really replicate easily how I wrote it before. You can, but so undefined at pi over 2 plus n pi, where n is in the set of integers. So that's where x is 0. And then the remaining two, cotangent and cosecant, are undefined where y is 0. So they're undefined at n pi, where n is in the set of integers. Look at us using our set notation from way back. Right? So what happens is we've got our sine and our cosine and our tangent. Those are our core three functions, right? And then we've got our cosecant, our secant, and our cotangent kind of hanging out. There's no harm in knowing those as well. But our main players are going to be sine and cosine and tangent, right? And so what happens is it can be really tedious to figure out, now it won't let me scroll, there we go, to figure out if I'm in quadrant 3, for example, then my x is negative and my y is negative, right? So then my tangent would be a negative over a negative, which would be a positive value. So that can get really tedious to figure out, okay, well, if I'm in quadrant 2, for example, then my x is negative, right? My x is negative here, but my y is positive, so then my tangent would be negative, right? And so that can get really kind of tedious and annoying. So we've got a fun little memory helper. Okay. So say p of xy is in Q2, then x is negative and y is positive. Okay. So tan of t, which is y over x, is going to be a positive over a negative, which is a negative number, right? So that's going to get really very tedious very quickly to figure out, okay, where are things positive and negative? Okay. It can get very tedious to try to find the sign, S-I-G-N, the sign of each of the 6 trig functions for each problem. So we can use this kind of memory helper. So we use this memory helper. I don't know what they're called, mnemonics. Memory helper, I think it's easier. Memory helper to remember which functions are positive in which quadrants. To remember which functions are positive, okay, in each quadrant. So if we break up our quadrants here, right, we've got our Q1, our Q2, Q3, oops, made it down low a little bit, Q4. Okay. So here what we have is A, S, T, C. Okay. And usually, I mean, there's kind of all kinds of things that you could use, right? You could, depending on if you took some sort of calculus before or pre-calc before, right? You might remember cast if you read it like this. I guess you could even muster a CATS, or reading from Q1 all the way to Q4, all students take calculus. Or I've also heard all suckers take calculus. So whichever you prefer. I'll say students because it's more appropriate. But as long as you have those kind of under control, right? So here we have all students take calculus. All students take calculus. Okay, and so what it stands for is all trig functions are positive in Q1, right? Because x is positive and y is positive, so there's no reason to get a negative out of there. But for s here, sine is positive. In Q3, tan is positive. And in Q4, cos is the only one that's positive. And you can confirm this, right? If you look at what your x and your y values are. So we are requiring that you're kind of really well versed with where is x positive and where is y positive and negative on the xy plane. So let's do an example using this. If we have to find, let me scroll. A cos of 2 pi over 3. Okay. 2 pi over 3. Well, if I've got the cosine, then I know it's just going to be x, right? So for cos of anything, it's just going to be the x value that 2 pi over 3 puts me at. Okay. So I'll just say x. And if I do my unit circle here briefly, okay, 2 pi over 3, 3 pi over 3 would put me at the halfway mark at pi, right? But it looks like I'm just pi over 3 shy of a full half moon. So what I have here is I have a reference number of pi over 3. Okay. Notice that I'm in Q2, right? So, all right. Well, from Q2, I know that only sine is positive, which means that my cosine is going to be negative. So in Q2, only sine is positive. So cos 2 pi over 3 is negative. Okay. Which you would find if you went through and figured out what this point is, right, and then translate it. So using pi over 3, and then you would find that pi over 3, right, has a terminal point of t bar equals pi over 3, which is at the point, so has a reference point of, a terminal point of, so 1/2 root 3 over 2. Okay. And so knowing that cosine is negative, right? Or if you transfer it into the second quadrant, either way, you know that cos 2 pi over 3. So cos 2 pi over 3 is negative 1/2. Okay. Since x is negative in Q2, but also sine is the only one that's positive. So we've got two things to kind of back us up on why it should be positive, or sorry, why it should be negative. All right, let's do another one. if we're doing the tan of negative pi over 3, okay, well, if I look at my circle here, okay, negative pi over 3 means I've moved a distance down of negative pi over 3. So then my reference is also, whoa, what happened here? Put me somewhere else. Okay, you're still seeing the screen, so that's good. Let me see if I can get back there. Okay, good. So my reference angle then is just going to be pi over 3. But knowing that I'm in Q4, right, if I go all students take calculus, I know only cosine is positive in the 4th quadrant. So I know my tangent is going to be negative. So what I have is the reference, or sorry, the terminal point of pi over 3, again, is 1/2 root 3 over 2. Okay, maybe I'll use a color here. In Q4, we have x is positive and y is negative. So what we have is we have 1/2 negative root 3 over 2. Okay. So the tan of negative, so we can use this, right? Because the tan of negative pi over 3, if you know what the terminal point of negative pi over 3 is, then you can say, okay, well, if I know my x's and my y's, wanted to show you what I'm referring to, y over x, right? Here, I want to make sure that x is not equal to 0. It's not in this case, so we're good. Y over x, which is going to be negative root 3 over 2 divided by 1/2. If I've got flip and multiply, then I get a negative root 3. Right. I just kind of go through all that work. Okay. Or what you can do is you can look at negative pi over 3 and say, well, pi over 3 is just going to be my reference angle, right? That's what we did over here, but we showed a little bit more work. And so, or since pi over 3 is our reference angle, oops, sorry, our reference number, there'll be angles soon enough, but for now, so since pi over 3 is our reference number, we can say that the tan of negative pi over 3 is going to be the same as the negative tan of pi over 3. The tan of pi over 3 is still going to be root 3, but then the negative on top of that, because we're in Q4. Good. Okay. What if we had to do, so that was B. Let's do a part C of this example. What if I have to find something like sine of 19 pi over 4? Okay. I'm going to do the same thing that I did before, right? Or you can use your calculator. 19 over 4 is going to give me what? 19 divided by 4, kind of ignoring the pi for a little bit, gives me 4.75. So 4 3/4 pi. So 4 pi plus 3/4 pi, Or if you prefer, and I prefer it, I just chip away and take away 2 pi as I go. So this is going to be the sine of 2 pi is going to be the same as 8 pi over 4. So 8 pi over 4 plus, so 19 minus 8. You can just do it behind the scenes on your calculator. 19 minus 8 is 11 pi, which means I can still pull out another 8. Plus 8 pi over 4 leaves me at 3 pi over 4. Okay. So this becomes my reference number. Or sorry, my terminal point. Right? 8 pi over 4, 8 pi over 4. This is just around the unit circle twice. Okay. So the one I'm dealing with is 3 pi over 4. 3 pi over 4 is in the second quadrant again. Just feels like it's always in the second quadrant. So if I go 3 pi over 4, it means I've got, oh, I went a little bit far. Why do I say that? Well, because I know pi over 4 is halfway. Okay. So my t bar is pi over 4, right? 3 pi over 4 just needs a remaining pi over 4 to get to 4 pi over 4, which is pi. So now that I know my reference number, right, t bar is pi over 4, which has a terminal point at pi over 4 is root 2 over 2, root 2 over 2. Okay. So now in Q2, right, we kind of have two options. All students take calculus, right? So here, all students take calculus. Sign is positive in Q2, right? Or if you prefer to kind of kick it old school, right, then I know that in Q2, my x is negative and my y is positive. So in Q2, x is negative and y is positive. So we have the reference, or sorry, the terminal point is at negative root 2 over 2, root 2 over 2. Okay. So if I'm talking about the sine, sine is the y, right? Sine t is y, right? So what we're saying is that sine of 19 pi over 4 is going to be root 2 over 2, positive. So there are kind of two ways that you can get to that positive or negative. Here I'm doing it kind of thoroughly, right? Where I'm convincing myself that, okay, x is negative, y is positive, sine is y, and so I get a positive value. If you wanted to, you could just say, okay, well, I know I'm in Q2, so sine is positive, I'm just going to take the y. Kind of more useful for things like tangent and cotangent. Okay. So you've probably used your calculator for trig functions before, and of course we can use our calculator for trig functions if it's not one of these core kind of check-in points, right? But those check-in points, pi over 6, pi over 4, pi over 3, pi over 2, and then the quarter-way marks, those are going to serve you really well, right? And so a lot of these problems that we do are just going to be in multiples of pi over 6, 4, 3, 2. But we should talk about how to use your calculator. So we can use our calculator for some calculations. But we need to make sure that our calculator is in radians, right? So your calculator is going to be either in radian mode or degree mode. And so, and there's usually, I'll try to show it on here. There's like a little R, there's a DRG up top, and it'll just highlight which mode you're in. So let me see if I can remember how to change the mode. Okay, so if you want to change the mode on this calculator, and most calculators are pretty similar, then you're going to go Shift Setup, okay, and it gives you the angle unit, so hit 2, and then you're going to select which one you want, degree, radian, or radian. We're never going to use radian, but we will switch between degree and radian mode. So you'll want to make sure you're in radian mode and just make sure that little R up top is highlighted. Okay? So, but we need to make sure our calculator is in radians, is in radian mode. Okay. So make sure you know how to get into radian mode and just kind of have a good handle on how to move back and forth. From here on out, if we're doing trig functions and there's no little degree marker, you have to be in radians. I know that's a hard thing, especially if you're just starting this stuff. How do I know if I'm in radians or degree mode? Well, unless there's a little degree, which is a little circle superscript, then you have to be in radians. Okay. So we only work Shift Setup 4. Shift Setup. Oh, the engineer symbol. What does that one do? I don't know what the engineer symbol does. To change it from radians to degrees, you go Shift Setup 2. So we only work in radians when using trig functions unless, okay, oh yeah, so figure out your calculator, right? On this one, unless they've updated it, they might have more options, but just figure out how to use your calculator and move into radian mode and back to degree mode. But for us, we're going to be working in radian mode. So unless you see a degree symbol such as 360 degrees. Oops. And that should be a hollow circle. Okay. So for things like 19 pi over 4, there's no degree symbol, so you know you have to be in radians. Okay. Before we go ahead and use our calculator for some of these calculations, we're just going to establish some of these fundamental properties of trig functions. So in order to use our calculator to find trig functions, we establish some fundamental properties. We establish some fundamental, I guess they're identities, fundamental identities. The first is in a section called Reciprocal Identities. Reciprocal Identities, which says that, okay, the cosecant of t, remember the cosecant is just 1 over y as long as y is not equal to 0. And then y was sine of t. So 1 over the sine of t. Okay. The secant of t, same idea as 1 over cos t. And the cotangent of t is 1 over tan t. Right. We'll also notice that tan t is sine t over cos t, right? Just using x and y, replacing it with sine and cos. So sine t over cos t, which if cotangent of t is 1 over tan t, then you have 1 over sine t over cos t. So then another identity for the cotangent of t is going to be cos t over sine t. Okay. So these are called the reciprocal identities. Okay. We're also going to establish the Pythagorean identities right away. So remember, it all goes back to a circle which has x squared plus y squared equals 1, or r squared for any circle, right? If x is cosine and y is sine, right? Then we have cos squared plus sine squared equals 1, right, on the unit circle. So we have our first Pythagorean identity is sine squared t plus cos squared t is 1. Right. This is from x squared plus y squared equals 1. Right. Switching x and y, but that's okay. Since we're adding, a plus b is the same as b plus a. So sine squared t plus cos squared t is 1. Okay. Some other identities that we're going to use quite a bit are tan squared t plus 1 is the secant squared t. Okay? We don't need to know, because these are being established as identities, we don't actually need to know where they came from. There are proofs, of course, some easier than others, but we're allowed to just use them. 1 plus the cotangent squared of t is the same as the cosecant squared of t. Okay. Here, we're going to use these quite a bit, so I'm going to try to highlight around them. Oops. I accidentally erased it all. Wink. Whoop. There. Okay. So these identities, right, we're going to rely on these quite a bit to solve problems. Okay. For example, pretty much all calculators, even this fancy-pantsy calculator, only has sine, cosine, and tangent, right? So it doesn't have cosecant, it doesn't have cotangent, it doesn't have secant, right? And so we need to be able to know how to get there. So, oops. Most calculators only have buttons for I'll do them in the order they appear: sine, cosine, and tangent. Okay. So we need to use the reciprocal properties right up here, the reciprocal identities, to figure out the rest of the functions. So we need to use the reciprocal identities to find the remaining functions. Okay. So, for example, use your calculator to find A, the sine of 2.2, right? Notice 2.2 does not have a little degree symbol on it, so we know we have to be in radians. Okay. If you just use your calculator, right, the sine, and then so you hit sine. Some calculators you have to do the 2.2 and then hit the sine button. Just get to know your calculator, right? We don't necessarily have the same calculator, so but we should all end up at the same number. And so I get that it's approximately 0.8084964038. Okay. So that's fine. Okay, hopefully that's what you're finding, right? We do these easy ones because I need to make sure that you know how to use your calculator. So what if we have to do something like the cotangent of 28? Again, there's no degree symbol, so I know I have to be in radians. Okay, cotangent, there's no cotangent button. And so what I need is I need to remember that cotangent is 1 over tan, right? So what I can do, this t and this t are the same. So what I'll do is I'll just rewrite this as the 1 over the tan of 28. Oops. Okay. Because I can find the tangent of 28. In fact, tan of 28 is negative 0.2814290. So this is roughly equal to 1 over negative 0.2814296. 2814296046. Okay. If you do 1 over that, then you should get roughly negative 3.553286448. Okay. You might be tempted to use the tan to the -1 button. That's actually the inverse of tan. So remember inverse functions, and we'll get to the inverse functions for trig functions, but remember the inverse functions are different from 1 over, right? And so this tan to the -1 on your calculator is actually the inverse function of tan, not 1 over tan. So I will write that here. Notice that on your calculator, the tan inverse button is not 1 over tan. Okay? You can try it. Try the inverse tan of 28. The inverse tan of 28, oops, is roughly 1.535097214, okay, which is not the same as the -3.55. This is the one I want to highlight. Okay. Which is not the same as 1. Oh, bumped me out again. Uh-oh. How do I? Not the same as, okay, I'm back, as 1 over the tan of 28. Okay. So that's just something to keep in mind, right? So I'll kind of emphasize that they're not the same, right? So you have to use the reciprocal properties. Okay. So let's do another example. Now we're just kind of expand on our knowledge a little bit and just kind of build out. So if I tell you, if the cos of t is 3 over 5 and t is in quadrant 4 and t is in quadrant 4, find the values of all trig functions at t. Okay, tricky. It's not as tricky as it sounds, but it's tricky because we haven't seen something exactly like it. So if the cos of t is 3 over 5 and t is in Q4, find all the values of all trig functions at t. Cos t is the x value, right? So if we know the x value, then that's good. That's one of the two that we need, right? Everything else is defined in terms of x and y, right? So I just need to find y, and then I'll be able to use x and y to find the other trig functions, right? So what we'll say is that since the cos of t is 3 over 5, okay, we know x must be 3 over 5. Okay. So we need to find, now we need to find y. Oops. Now we need to find y. How are we going to do that? Okay. Well, one of the things that the most common thing to use is this Pythagorean identity, right? Sine squared t plus cos squared t is 1. Okay. Use sine squared t, plus cos squared t is 1 to solve for sine. To solve for sine of t, which is y, right? Or you could bounce it back to x squared plus y squared equals 1. That's fine too. You're doing the same thing, right? But because it's going to be nice to have it in terms of sine, I'm just going to work in terms of sine. But we are doing the same thing as x squared plus y squared equals 1. Okay. So one thing that I want you to note is that this 2 is allowed to move outside. So that's kind of weird because often that's not the case. Here, I'll make a note over here. Note, sine squared t is the same as sine of t squared. Cos squared t is the same as cos t squared. Okay, so you're allowed to bump it out, and it works for all the trig functions. If it's squared, then you can bump it outside, which is not always the case, right? So that can get confusing, right? But now we've established that we're allowed to do that. Okay, so what we'll say is that sine squared t plus, and I know cos t is 3 over 5, so what I have is actually 3 over 5 squared is 1. Because I'm dividing inside 3 over 5, I can bring that square inside. So I get sine squared t plus 9 over 25 equals 1. Okay. Because I anticipate moving this over here, I'm trying to solve for sine, right? So what I'm going to do in this step is I'm going to multiply 1 by 25 over 25 to get that common denominator already. So what I get is I get sine squared t is 25 over 25 minus 9 over 25. So sine squared t, 25 minus 9 is 16 over 25, right? Subtracting fractions, I have to have a common denominator, and in this case, it's 25. So now, if I need to solve for sine t, I can take the square root, remembering that when I take the square root, I get the positive and the negative result, right? And so I get sine t is the plus minus square root of 16 over 25. That square root can get split up because I'm dividing inside. And so sine t is the plus minus of root 16, which is 4, over the root of 25, which is 5. Okay. And this is equal to y. So y is plus or minus 4 over 5, depending on where we are on the unit circle. Now, we know from the question that we're in Q4, okay? So in Q4, y is negative, right? In Q4, y is negative. So sine t is negative 4 over 5, which is going to be your y. Okay. Now that we know that x is 3 over 5, yep, and y is negative 4 over 5, we can establish the remaining trig functions. So now that we know x is 3 over 5 and y is negative 4 over 5, we can establish the remaining trig functions. Right. And this is just the same thing that we did earlier today. Right. Uh-oh. I mixed up all my... I just want to have it for reference. Where is my... I didn't highlight them in here, did I? There they are. Second page, of course. So let's just remember, I'll write them down so that we have them, right, as we go. So sine t is y. So, right, we're only talking about cos t. We don't actually know what t is, and that's okay, right? But so what we have, and find all the values of all trig functions at t. So some general t. So sine t is y, which we just found was negative, I'll put it down below, negative 4 over 5. We also know that cos t equals x, which was 3 over 5. We know that tan t is y over x, as long as x is not 0. In this case, x is 3 over 5, so we're safe, right? We're not giving some undefined number. So y in this case is negative 4 over 5 divided by x, which is 3 over 5. Fraction over fraction, I'm going to flip and multiply. And so I get negative 4 over 5 times 5 over 3. 5s are going to cancel, and it puts me at negative 4 over 3. Okay. The next trig function I'm going to find is the cosecant of t, which is 1 over y. 1 over y in this case is 1 over negative 4 over 5. Flip and multiply, right? 1 over 1, it's just 1. And then negative 4 over 5, if I flip it, I get 1 over 1 times 5 over negative 4. So I get negative 5 over 4, right? That negative can just kind of float around if you wanted to. Good. How about the secant? Secant of t is 1 over x, as long as x is not equal to 0. X in this case was 3 over 5. So we have 1 over 3 over 5. Now I'm just going to move a little bit quicker. I get 5 over 3. And finally, cotangent of t is going to be x over y, which is going to be 3 over 5 over negative 4 over 5. If I flip and multiply these, I get 3 over 5 times 5 over negative 4, which is the negative 3 over 4. Okay. Notice that, oops, these have just been flipped, right? You can find other relationships too, right? Like this one and this one, right? So they're definitely related, and they come from that reciprocal property that we just talked about, right? But it's just as easy, I think, to just go through and just find them using x and y, right? Gonna get to the same place. Good. So Let's see here. For example, so another thing that we could do is we could rewrite a trig function in terms of another trig function. Okay, so I'll just start. We can use the trig identities. We can use the trig identities to rewrite functions, to rewrite trig functions in terms of other trig functions. So for example, if you have to write tan t in terms of cos t, where t is in Q3, where t is in the third quadrant. Okay, so we need to think about this a little bit, right? Let's see here. If I write my quadrants out, I've got my, oops, don't know why I started there. All students take calculus. So in Q3, okay, yeah. Sorry. Just looking at my notes here. In Q3, 10 is positive and all others are negative. Okay. So that means that cos and sine are going to be negative in the third quadrant. Okay. So now what I'm going to start out and say, and there are a lot of different ways that you could develop this, right? If you have to rewrite tan t in terms of just cosine t, so eliminate all other things, well, we can start and say tan t, let's just start with a pretty basic identity, is the same as sine t over cos t. And so already, right, I've got my cos t, that's good, right? In terms of cos t. And then here, this we're gonna write in terms of cos t. Right, so we're gonna rearrange everything until we are only working in terms of cosine of t is what this question is asking us to do. So what I'm gonna do is I'm gonna transform sine of t into something that is related to cosine of t. So what we'll use is that, okay, so we need to rewrite sine t in terms of cos of t. In terms of cos t. Okay. Well, we can look at some of these identities that we have, or all of them, rather, right? I've got some options, and this is more of a puzzle game than anything else, right? And so here I've got a sine t. That's not going to help me much, right? Because I need to have a sine t that I can convert into a cosine. The one that kind of strikes my fancy is this one, right? Where I've got sine squared t plus cos squared t is 1. That's going to be a really useful identity to kind of remember and have up our sleeve. We use it a lot. So we can write sine squared t plus cos squared t is 1. So again, I'm going to solve for sine t here. So sine squared t is 1 minus cos squared t. Okay? All I need to do is take the square root, and then I'll have sine t. But remember, I get the positive and the negative values. So then sine t is going to be plus minus square root of 1 minus cos squared t. Here, we need to remember that in Q3, all others are negative, right? So sine t is going to be negative. In Q3, sine t is negative. So then we have sine t is negative root 1 minus cos squared t. So that's what I'm going to transfer to what I started up here. Right? So now we can write tan t is sine t over cos t, and sine t is being replaced by this guy here. So I get negative root 1 minus cos squared t divided by cos t. Noticing, right, tan is positive in Q3, but sine t is negative and cos t is negative, so negative divided by negative gives me a positive, so I'm safe. Okay? So this now in terms of cos t, right? The only t's I have in there are related to cos t, right? 1 minus cos squared t and cos t. Okay. Good. All right. Not really a time to start a new section. So, okay. We'll start, we'll do graphing next day. It's not going to be, we're not going to go too deep into it. But then we'll have a pretty good hold on trig functions. Are there any questions before we go? I'll stop the recording.